Hello everyone. So in this lecture, what we are going to learn is some mathematical aspects of casting process. Okay. So what can be the mathematical aspect? Casting is about pouring liquid metal inside a mold and then solidifying it, right? So there are few aspects here. Number one, we are dealing with liquid metal or liquid materials. So in that case, we need to understand some aspects of the fluid flow. And number two, also some solidification related things. So in this lecture, we are going to talk about the fluid flow related things. And whenever we talk about fluids, there is one very fundamental principle, which I don't know if you know about it or not, but we will discuss it briefly anyway. Bernoulli's, equation or Bernoulli's principle. Okay. So what is Bernoulli's principle? Well, this is a very simple thing which says that if there is a stream of any fluid, and you have different diameters, let's say think of it as a pipe, if you have different diameters of the pipe, then there is some relationship between the pressure and velocity at different points in that pipe or in that stream of water. Okay, so basically you must have all experienced that when when the pipe is thinner, then you have a higher pressure of water, right? And when if the same stream becomes, the pipe becomes wider at some point, then the pressure goes down. So this is as simple as that. Basically, when the speed of or velocity of a liquid increases, then the pressure decreases. That is basically your Bernoulli's principle. Okay, so how do we mathematically express this principle? I will not go into the derivation, but I will just write this down for you. So what this principle says is V, if V is the velocity of the fluid, in that case, square V square by 2 plus G, which is the gravitational constant, H is the height of the liquid column, plus the third term is pressure divided by the density of the liquid. This summation always remains a constant. So that is basically your Bernoulli's equation. Okay, so let me also quickly write down. V was our velocity, G you know already, H is the height of the liquid column, then P is the pressure, and rho is the density of the liquid or fluid. All right. Okay. So now let us apply this to the casting process. Now, what do we do? First of all, we need to take a very simple case. The simple case here is, let's say you have a mold and you're pouring the liquid metal on top of it. Everything is at atmospheric pressure. So we are basically now going to assume that the pressure is constant throughout. Now, let me draw some simple let me get some lines. Yes, so I'll draw a very simple mold. Let's say this is your mold, and you have a sprue here through which you are going to pour your liquid metal, and there is certain level of filling. Okay, now in this sprue, let's say this is your liquid metal. Okay, all right, so there are different points here, and now here let's say this is your mold. Inside the mold you have some sand or whatever, something filled in. Okay, and then you also have certain structure here and so on. This is your gate, this point. Okay, this is your gate. Okay, now I will take any 3 points and evaluate the velocity of the liquid there. So number one, this is my point, and by the way, I am assuming that I am maintaining this level of liquid. So this point is maintained. This level of liquid is maintained by refilling the metal. So as soon as my metal goes out and it goes inside the mold, then I pour more metal and always maintain the same level. What I'm also assuming is that everything here is at atmospheric pressure. So basically all points 1, 2 and 3 all at atmospheric pressure. All right, so points, yeah, this is your point 1 and this is the point 3 is basically your gate. Okay, so now let's apply Bernoulli's principle. Let me also write a few more names here. This is your mold and this is your sprue. Okay, and the rest you know already. Okay, so now let's apply the Bernoulli's principle here. Point number 1. What do we have at point number 1? We have a certain velocity, let's call it v1. Okay, v1 square divided by 2 plus g into, well, what is h above point 1? That is 0. So this is 0. Why? Because there is no liquid column above point 1. Okay. However, that is not the case with 3. So we are comparing points 1 and 3. 1 and 3 here. Okay. So there is, this quantity goes to 0 anyway. Plus now we have P1 divided by your density of metal. Now since as per the Bernoulli's equation, they are all constant at point number 1, point number 3, this summation is constant. So we will equate it with point 3. Okay, what do we have at point 3? We have some velocity called v3 and divided by 2 plus g. Now here we have certain height. Now this height here, let us call it h total. So we don't get confused with other heights. This is your h total, that is the liquid column height. So that is your GHT plus, again, the pressure here, P1 and P3 are the same because they are atmospheric pressure, right? So P1 equals P3 equals P atmosphere. What is also equal? No, that's all. These are the two things that are equal. Rho is of course the same, right? Because it's the same metal. What does that mean? That this and this also will cancel out, these two terms. Now what do we have here? So this term is 0, this term is cancelled out. Now if you wish to, now by the way, so here what is V1? V1 is also 0 because at that point we are just maintaining a certain level and there is no particular velocity in the fluid. So at V1 point, this is also 0, right? So V1 is also equal to 0. So basically this entire term, the second term, again V3 square divided by 2 plus GHT will be equal to 0. Now this G here, G is always negative, right? Because this is a free falling, this is a liquid is falling down. So this is always negative. So basically this is how it is, right? So now what do we get here? V3 square by 2 equals GHT, which means V3 equals square root of 2GHT. Now this is something, this formula you must have also learned somewhere else, but I just wanted to mention that this is how we can also calculate the velocity of liquid at any given point. So basically you need to find a couple of points and find, typically the easier way would be to find the points where the velocity is 0 or the liquid column height is 0. In that case you can just compare these and then find out the velocity at any certain point. In some cases, the very simple cases, you can just use the velocity, this formula directly. Now by the way, V3, I told you that 3 was also a gauge, so we can also call it VG, and this is the formula for your VG. Okay, there is one more small thing that I would like to mention here is the time for filling the mold. So how do you calculate the time? Normally, this is the volume. V equals the volume of liquid. Volume divided by the cross-sectional area plus velocity. So if I say A is the cross-sectional area of your design of your mold. So cross-sectional area of the gate actually. So design, when I said it, basically it is the gate and the velocity at the gate. So velocity of the gate you have already calculated now at gate. All right, cross-sectional area of gate. Okay, so what will that be? That will be your VG multiplied by some AG. So AG in most cases will be given to you or you can geometrically calculate. So these are the two things. And now we will move on to a little more complicated case where you don't have the atmospheric pressure everywhere. All right.